then moved fields into climate physics, which he's been working on ever since. He's currently a research fellow at Jesus College in Oxford and a member of the physics department. So Kristian, do you want to try and share your screen with us?
Yeah, let's try it out.
Great. So as usual, we like these seminars to be relaxed. So please do put your questions in the chat throughout, and then I will interrupt Kristian and ask those questions. And then otherwise, we'll also have a session of questions at the end. Great. So Kristian is going to speak to us today about circulation regimes. So take it away, Kristian.
Great, let's start my timer. Okay, thanks very much, Hannah, for the introduction and for the invitation to speak here. It's a pleasure to do so. Yeah, so I was asked today to speak about so-called circulation regimes, and I'm going to try to cover quite a wide range of aspects of regimes, all the way from some kind of foundational ideas using topology all the way up to hopefully something about what the CMIP6 models think about these circulation regimes. It's quite a bold agenda, or especially given that Hannah has informed me that I can expect the audience to ask lots of questions, which makes it perhaps a bit more foolhardy than bold. But I am expecting the questions, and you should just ask for clarification when you want it. It's mostly otherwise going to be more about the ideas and less about the nitty-gritty details. So just ask if you really do want some of the nitty-gritty details. Yeah, just to quickly acknowledge my funding, very generous funding from Thomas Phillips and Jocelyn Keane Fellowship, and also the collaborators, colleagues I've worked with. So I'm going to basically be describing work that I've done with a lot of people over the last 3 or 4 years, say the most important ones I've listed here. Okay, so what am I going to try to do in this talk? I'm basically going to try to give my own perspective, I guess, on the following 3 questions. Firstly, what even are regimes at all? Secondly, are these just some kind of interesting abstract idea, or do they actually provide some helpful information in practice? And finally, what do climate models actually have to say about them? And of course, what we're all ultimately interested in there is, how are these regimes going to change with climate change, and can we understand climate change using this framework? So to understand the idea of regimes, it's helpful to just jump straight into the motivation, which is essentially, and for my purposes, the mid-latitude circulation, or specifically the northern hemisphere mid-latitude circulation. So what's being shown in this video are geopotential height anomalies at 500 hectopascals in the winter of 2017. And you can see that it's a swirling, complicated, and chaotic mess, right? But of course, we're all very interested, especially those of us who live in the northern hemisphere mid-latitudes, we're very interested in understanding this circulation. We want to be able to predict it, in particular, as far forward in time as possible, and also understand how it might change in the future. But it turns out that doing so is about as hard as you might expect from looking at this video. But essentially, the way it happened is that after staring at these kind of figures for many years, meteorologists started noticing that you would have certain patterns, certain circulation patterns cropping up again and again. And this quickly led to the idea of regimes, which is essentially, perhaps we can approximate this complicated flow as a Markov chain with a very small number of states or regimes, and in some way capture all the relevant variability and dynamics using just a much more simple Markovian framework. Oh, Can we switch slides? Oops, there we go. Yeah, so the quintessential example of such a kind of regime view of the North Atlantic in particular is the so-called North Atlantic Oscillation, pictured here. It's basically this dipole. You're probably all familiar with this, a dipole of pressure anomalies, where this is showing the negative phase of the dipole, and then the positive phase, you just flip the colors. And it turns out that this dipole is a pretty decent approximation of European winter weather, also to a lesser extent Eastern North American weather as well. So this is a kind of great example of a two-state regime picture of the North Atlantic. It basically explains a lot of variability, and there's a very few number of states, just 2 states. If you're not familiar, in case you're not familiar with kind of why things like the NAO do really affect surface weather conditions, we had a great example here in the UK a couple of years ago in the winter of 2020. This is what the pressure anomalies looked like that winter, and it was a very strong positive NAO phase. To understand why that really affected winter in the UK in particular, I always find it a bit easier to flip from looking at pressure patterns to looking at what the winds were doing, and in particular what the jet stream was doing. And this is what the jet stream looked like that winter. It's in red there, and you can see it was basically pointing directly at the UK. And what that means in practice is that every time you get a storm developing over the Atlantic Ocean, it just gets sort of sucked into the jet stream and spat out onto the UK. And we had a really miserable winter that year with a considerable amount of flooding. Okay, so this idea of regimes first came up in the 50s, I think. But 70 years later, there's still no agreed upon definition of what actually does constitute a regime at all. There have been several attempts to come up with some kind of objective computation. The most common two for the North Atlantic are, well, firstly, you can do k-means clustering algorithms, where you just take your favorite pressure fields or wind fields, and then you do some kind of k-means clustering on the phase space, usually after having taken a principal component, an EOF decomposition. And then typically you get the most common thing you get are 4 pressure patterns shown on the right, which include the NAO phases, and then also a Scandinavian blocking regime and some kind of Atlantic ridge. But actually, if you look in the literature, depending on exactly how you do this, you can get anything between 2 to 6 patterns, and in fact, sometimes many more, depending on where you look and how you do it. The other way of doing it is to basically kind of stare at things long enough to have an idea for a much more bespoke diagnostic, and this was famously done by Tim Willings and others in 2010, where they showed that the jet stream, which we were just talking about, shows some kind of multimodality. It has preferred latitudes that it likes to sit at. So that gives you some kind of jet latitude regimes. But the point is, right, that none of these, depending on how you do it, right, you get a different number of regimes that are slightly different from each other. And while they're all related, they're not kind of easily comparable. And certainly the way in which you've obtained these are not equivalent. The other complication is that people don't just look at regimes in the sort of atmospheric data. It's also been studied a lot in simpler nonlinear dynamical systems. Of course, most famously, you've got the Lorentz 63 butterfly on the left there, which was kind of, I suppose, crucial in convincing people that maybe this idea of circulation regimes has some dynamical and theoretical basis, right? Because the Lorentz butterfly is a great example where everyone can look at it and say, oh yeah, you've got 2 regimes corresponding to the 2 wings of the butterfly. A little later, Charney and Devore came out with their their model, their simplified model of the atmosphere. So this is the phase space I've plotted here. It's truncated to the first three principal components in each case. It's much less easy to see what's going on with the regimes in shiny dwarf, but there are two regimes there too, it turns out, one of which corresponds essentially to the kind of dense central region, and this other regime corresponds to all these looping, these thin loops moving out around it. And then finally, Lawrence introduced another system in '96, the Lawrence 96 system, which I'll talk less about, but basically it's a kind of swirling mess of spaghetti, of wave-like spaghetti, where Lawrence himself diagnosed two regimes, which I'll talk more about in just a sec. So, okay, if you wanted to come up with some kind of more objective mathematical even definition of regimes, you have to somehow figure out what all these systems have in common with each other. And what happens is, if you take any of the usual definitions from the literature, they will inevitably fail to include one or more of these different states from the definition. So, for example, people often might define regimes as being characterized by having above average lifespan, or maybe they are high density regions in phase space, so some kind of multimodality. Or maybe you want to define it using phase space velocities, right? But if you take any of these definitions and try to apply it to all of these four systems I've shown, you will inevitably exclude one of them. Essentially, the Charney divorce system is kind of weird enough by itself to exclude many of these things, because essentially one of the regimes, as I mentioned, is this very high density region with very slow phase velocities, and then the other regime are these very low density loops that have very high phase speeds. Okay, so one possible response to this mess is what I kind of like to joke as the regimes as pornography perspective, right? So you might have heard about this famous court case where Supreme Court Justice Stewart admitted that he couldn't actually give a definition of what pornography was, but nevertheless he knew what it was when he saw it. And maybe you take the same perspective on regimes, right? Okay, we can't define them rigorously, but they are a useful concept to have floating around to capture kind of a lot of different ideas, and we know kind of what they are when we see them. But coming from a maths background, that doesn't seem very satisfying to me. And in practice, what I've noticed is that if you kind of take this attitude, when you talk to meteorologists about regimes with this kind of attitude, you will quickly end up in arguments about whether the regimes are actually real or not. And if a meteorologist doesn't think these regimes are real, then they aren't going to care about using them, which is fair enough, really. So can we do any better? So in terms of the work I did in my PhD, none of it ended up being applicable really to my subsequent climate work, but there were two kind of more broad lessons which I've taken with me from pure maths, which I do think have been very useful. The first of which is that the kind of abstractions you get, and which are ubiquitous in pure maths, they're not just kind of fun, esoteric games, but they are actually really helpful. You usually almost always get some reward, some practical reward for having done a good abstraction. And the second useful lesson is that it's often helpful and useful to take a kind of childish idea deadly seriously, to not just kind of have the idea and then wander off, but to really pursue it to its ultimate, take it to its logical conclusion. So how might we do a kind of childish abstraction of the atmosphere in the context of regimes? Well, after staring at these phase spaces of these different systems for a while, you might come to the conclusion that basically they're all just combinations of connected regions and some kind of loops, which are all examples of non-trivial topology. So of course, famously, topology is a field where you can't distinguish between a coffee cup and a donut, right? Because they're both, topologically speaking, characterized by the fact that they're connected surfaces with one hole or one loop in them. So connected components and loops, these are the kind of things which are topological invariants, and you can classify them using Betti numbers if you've come across that. Just to say, I've written this phrase modular density up there, and the point being is that you just sort of have to keep in mind that with all these systems, which are of course continuous dynamical systems, any of the structure that you're looking at is always kind of modulo some, or implicitly modulo some density threshold. So for example, if you take the Lorentz 63 butterfly, right, everyone knows that if you take a generic finite sample, you're going to see two holes. But in the limit of infinitely many points, you wouldn't see any holes because they would have closed up completely. And the point, of course, the sort of simple point is just that the holes correspond to very low density regions in phase space. So of course, when you take infinitely many points, you will eventually have trajectories that go all the way into the center. And you wouldn't see any holes, right? But somehow, we want to keep the holes as a characteristic feature. So you have to impose some kind of density thresholding, and you can do that in a straightforward way, which I won't really go into unless anyone asks me about it. But anyway, that's the idea, to think about all these regimes as being characterized by some kind of non-trivial topology. Now, that's just a fanciful idea, but it turns out that there's a very nifty tool which can make this idea practical, and that's the tool called persistent homology. And essentially, it's an algorithm which can compute for you loops and connected components in an arbitrary data set, just using linear algebra. So homology is just is basically just computations with matrices, big matrices, and it will spit out something about, you know, the number of connected components, the number of loops, and you can even, and once you have that, you can very easily compute actual representatives of these components and loops. And the nice thing about this algorithm is that you don't need to put in any prior choices, unlike, for example, with k-means clustering, where it can be extremely difficult to justify the choice of k. You know, how many clusters are you going to do you want to produce? Very difficult to justify, and you have to specify it up front. While with topological methods, you don't have to do anything like that. You just put in your data set, and it will attempt to, it will look and give you the relevant non-trivial topology. So just briefly, how this works. Essentially, what you do is, okay, a data set, a point cloud data set by itself has trivial topology. It's just a bunch of disconnected points. And the way you get around this is to just thicken each data point. So you basically imagine putting a little disk of some fixed radius around each point. Now all of a sudden you've got a non-trivial topological space, and you can compute the homology of that space. And then you just let the radius of these disks slowly increase. And by doing that, you can compute a filtration of homology groups, so just a sequence of homology groups. And finally, then you inspect the topological features in this filtration that are kind of hanging around for a long time. The idea being that the persistent topological features are the ones which are somehow capturing relevant dynamics. And I'm showing you examples now. So the plots have become more colorful, and it's basically showing you the actual algorithmic output of some persistent homology algorithms that have been used to actually find loops and components in these data sets. So, you know, in Shiny Devore, you get this very nice, you can make these very nice colorful plots of lots of nice loops. Lawrence 63, you of course get the two holes you expect. With Lawrence 96, it turns out that the two regimes that Lawrence himself classified in this system correspond essentially to the loop around the outer perimeter, and then the second regime corresponds to the hole, the low density hole in the middle. And then finally, the North Atlantic jet you can realize as some disconnected components. I think I saw some chat message come up, but Hannah, maybe you can ask questions for them if it does come up.
Could I maybe ask a question?
Yeah, go ahead.
Can you explain a bit more detail how you compute those curves and those homologies? So as I understand, you take clouds of points and you look at a ball, how many points are in there, and you call them connected. So how does that depend then on the ball of the radius? That's I guess that's what you must be using, right? Can you expand a little bit on how you do that?
Yeah, so essentially, once you fix the radius, then yeah, of course, every point that lands inside, points end up being connected, like, so anything which is within the radius of another point end up being landing in the same connected component. So you immediately get like lots of connected components, but you will also get some kind of, you might get loops and holes appearing. Of course, it depends entirely on this radius you've chosen, but that's somehow the point of persistent homology, is that, well, you overcome that problem by just computing this for many different choices of this radius. And then somehow the point is that the really striking features of your system will be there. You'll see them for a wide range of radius. So for example, the Lawrence 63 butterfly, if you imagine putting little disks around each point there, you are going to quickly connect up. You're immediately going to connect every single point, but you are still going to get holes. You're going to get those holes in the middle for every radius until you've somehow got a radius that's so big that you span the entire hole. Yeah, does that clarify a little more?
Yes, thank you very much.
There's a couple more in the chat, so maybe related. So Gemma asks, how do you choose the initial radius for the thickening, and what counts as persisting for a long time?
Yeah, good question. So the initial radius is basically, you can take it to be extremely small. These algorithms turn out to be very efficient. So essentially all you need to, like, a principled way of choosing it is to just, for example, you look at the minimum distance between any 2 points in your data set, right? You're not going to get any information from working with a radius that's smaller than that. So that's where you could set your minimum radius, and then you just expand it, and then you stop. You can just stop once every point is connected to every other point, then you can stop, because you're not going to get anything else at that point. Sorry, what was the other question again?
Yeah, so Gemma's second question is related to the other question. So Gemma asks, what counts as persisting for a long time? And we have another question from Martin, who says, won't specifying what persist means be akin to the K in K-means clustering?
Yeah, so essentially, yeah, there's a little bit of interpretation involved there. It can depend. So my colleague Nina, who's the topological data analysis expert, has sort of told me that depending on the application, the region where you want to have topological features might vary a bit, right? Because you might have some prior information about the structure, right? So for example, these kind of these kind of persistent homology algorithms are also used in places like chemistry, right, where you want to kind of measure some other structure of molecules and things like that, and you might have some prior information about, you know, how big these molecules are and so on, and that so you kind of know on beforehand what radiuses you want to focus on. Here, for the application to these kind of dynamical systems,
I'm not sure if we've lost Kristian.
Yes, I can hear you, Hannah, but not Kristian.
Okay. Oh, I think we've lost him. So
he told me that he has a second laptop, so if something broke, he has some backup, so he may wait a minute or so and he'll be back.
Yeah, let's do that.
There he is.
Hello again. Sorry about that. My laptop decided to crash in the middle of the talk this time, as opposed to at the end. Let's try sharing again.
Oh, great that you came back so quickly.
Yeah. Well, so I had my other laptop ready. Sorry about that. Where were we? We were here. Yeah. So basically, the question, right, was, okay, how do you justify, you know, how persistent these features should be, etc. And what I just say is that, well, essentially, it's not. There's work to be done, basically. The perspective we've taken so far is just that, well, with persistent homology, you can just compute all of the topological structure, and then you can just look at it. You can look at all the structure which emerges, which is clearly non-trivial in the sense that it's nothing like you would get just from Gaussian noise. And as long as it persists for a decent amount of time, then, you know, it's probably somehow meaningful, and then you can just look at it and see what it corresponds to. And it turns out that in all these systems, the features that persist for any decent length of time end up actually corresponding to the regime structure that you somehow expect to find in these regimes. So I realize that's slightly cop-out. Hopefully I'll be able to give you a better answer sometime in the future.
We have one more question on these slides, but people are thanking you for your thorough answer. So there's a question about what is the precise criterion for the colouring that you've done here? So for example, in Rent 63, why does the coloured region not cover larger parts of the butterfly wings?
Basically, so what's being plotted there is essentially the representatives of the two longest lived loops in the system, and the algorithm which computes these representatives, it turns out that computing representatives of loops is quite a difficult problem still. The algorithms and the software used to compute those representatives is still very much in its infancy. I've shown you an example where it did a really quite good job of kind of getting loops which roughly cover the holes, but it's definitely the case that in a more complicated situation, you might get loops which look a lot less optimal, let's say. So yeah, it's just slightly software dependent, but yeah. Okay, shall I move on, or was there something else?
Yes, I think that's all the questions for now. So thanks.
Great. Okay. Oops. Here we go. Okay. So what I might suggest is, okay, these ideas are still very much kind of in their infancy as well, I suppose. But I might suggest that this abstraction gives some insight into what regimes really are, and perhaps what we're all trying to what everyone's trying to capture in all these systems is just manifestations of non-trivial topology of your attractor. And it turns out that persistent homology is a very principled and very computationally efficient way to do that. And I should emphasize the computational efficiency, because somehow that's the reward you receive here for doing this level of abstraction, which is that there's no curse of dimensionality when it comes to computing homology groups. It really doesn't care much about how many dimensions you have in your system. The scaling is at worst linear in the number of dimensions, which is great news if you want to look at big climate data sets where you inevitably have to use very many dimensions, and with almost any other method to compute regimes, the high dimensionality will really ruin your day. So, okay, back to the real world. So that's the kind of abstract foundational idea, but there's still essentially the software. So I think this is a really promising way to look at regimes onwards, but a lot of the software is still just a little too new to be applied to the full climate data set, although we do hope to that this will change over the next year or two. So let's come back to the real world and this question about the Markov chain approximation, and just think a bit about, does it actually help us at all? Because you might be thinking, well, okay, that's very neat. You get some nice plots and topology, and it's all very cool, but do we actually gain anything practical from a Markov chain approximation? So just to point out, like, the maths, that's the kind of simple maths of the Markov chain approximation. So say you've got a bimodal view of the atmosphere, two states, two regimes, A and B, with some associated persistence probabilities, P and Q. And you've got some metric you're interested in. It might be the NAO, or it might be, you know, surface temperatures over Europe or whatever else. And you know something about, right, what kind of values your metric tends to take when you're in regime A, and what kind of values your metric takes when you're in regime B. If you know that, then you can compute the long-term mean of your metric of interest. It's this formula MA pi A plus MB pi B, where MA is just the mean value of this green arrow, so the mean value your metric takes in regime A, and it's similarly for MB. And these pi's are just the long-term proportion of time spent in each of the two regimes. So this formula is kind of obvious, right? Somehow the long-term mean is just determined by how much time you spend in each of the two regimes, right? But I've wanted to kind of spell out what these formula are, because it's obvious from looking at this that the total value of your metric of interest is a non-linear combination of persistence probabilities. And this is going to be a really sort of key observation to keep in mind in just a little bit. Does it work in practice? Okay, well, so the first kind of, the most famous example in sub-seasonal forecasting came, I think, from a paper by Cassou in 2008, which spawned a lot of follow-ups. And he showed that the MJO, which, if you don't know, is just some kind of organized tropical convection, this modulates regime occurrence rate. So basically, the way it works is if you have tropical convection in a certain region, then you can expect the regime occurrence rates to change a week later in the North Atlantic. And this is really was really a useful idea, because these regimes strongly affect renewable energy demand in Europe and North America, essentially because these regimes strongly modulate, how windy it's going to be or how sunny it's going to be. And of course, that strongly affects your renewable energy availability. And the result of this is, anecdotal evidence suggests that hedge funds will very quickly try to hire you if you know anything about how to do this. And of course, if the market thinks that this is worth spending money on, then it probably means that it must work somehow. In seasonal forecasting, for some reason, this hasn't really taken on so much in seasonal forecasting yet. I'll give my perspective on why just a little later. But it turns out this works equally well in seasonal timescale forecasts. So when you want to predict, months ahead in time, and in particular things like the winter NEO, which we talked about at the beginning of the talk, which strongly affects winter weather. You can account for, you can give good winter NEO forecasts using this regime framework, using Markovian dynamics. And in particular, I don't really have time to go into this, but you can not just explain the skill that we see our models having. So our models are able to predict the winter NEO with a decent level of skill, and you can explain that skill using regimes. The models also show a kind of weird feature you might have come across, usually referred to as the signal to noise paradox, and essentially amounts to just the fact that the model predictions, like the signal to noise ratios that the models have, are much smaller than they should be, given how skillful they actually are. So it's like the model is very underconfident in its predictions. And it turns out that this signal to noise issue is just, it's a standard feature of these kind of Markovian dynamics. As soon as your model, your forecasting model, has any kind of regime persistence bias whatsoever. So a kind of simplified picture might be that if your regime is like a potential well, then your model potential wells are quite shallow, while the real ones are quite deep somehow. Okay, so that's, okay, maybe you're thinking, okay, well, maybe you can explain some stuff, but couldn't we explain all of that stuff using just linear methods? Like, what are we really gaining here by moving away from things like linear regression to this kind of regime-y Markovian framework? And I'll try to emphasize two aspects, although I might just have time for one of them. The first one, which I think is the really crucial one, is that the Markovian framework allows you to account for non-linearities and asymmetries in a very straightforward way, which you sort of by definition can't do using linear methods, or not very easily anyway. And the second is that this idea of regimes very easily motivates a process-based understanding of predictability, essentially because if we saw earlier that the formulas that determine the long-term behavior of your kind of metrics of interest in a regime system, these are determined by the persistence probabilities. And if regime persistence is somehow what's driving things, then you quickly are going to have the idea that things like transient eddy forcing and feedbacks are playing a crucial role here, which I'll try to give an example of just a little later. So let's think about the nonlinearity then. Suppose you're interested in the North Atlantic, and you take the view that the regimes in the North Atlantic, we want to think about regimes using these jet latitude regimes. So just to spell out how that works, this was done by Tim Wollings in 2010. Essentially, you just track the latitudinal position of the jet every day, and then you just plot a histogram and look at the PDF. And it turns out that if you do that, you get 3 clearly defined jet latitude peaks corresponding to 3 preferred regimes where the jet likes to sit. So suppose that's your regime system, but what you're interested in, the metric of interest for you is the winter NAO. So if that's what it is, you need to figure out how the NAO relates to these jet latitude regimes on daily timescales. All these regimes are happening on daily timescales. And it turns out that this relationship between the regimes and the NAO is very visibly non-linear. So I've got latitude, the jet latitude on the x-axis here, and the NAO index on the y-axis, and I've colored the regimes in so you can kind of see where they are. And the point is just that you get this very striking non-linear relationship. Of course, with a Markov chain, this kind of regime picture, this kind of non-linearity is very easy to incorporate into your models, but not possible to do using just linear regression. And the way people have gotten around this, and probably the reason why Markovian this Markov ideas haven't been used in seasonal forecasting so much, is because if you take seasonal means of the previous picture, you get something which looks now roughly linear, right? So you smear away all the interesting non-linear information, and now you can do linear regression. So this is what people usually do. You look at correlations of seasonal averages and try to understand. But I would suggest that by doing so, you're killing a lot of interesting information, which probably we should be incorporating into our analysis. A second crucial way in which regimes allow you to account for non-linearities is teleconnections, right? There's a lot of interest in how things like ENSO, for example, influences the North Atlantic. But it's not straightforward to do this. If you look in the literature, there's a considerable amount of literature doing this and no kind of conclusive answers really yet. And I might suggest that the reason for that is that ENSO, things like ENSO, doesn't necessarily project directly onto, say, the NAO, but it projects onto particular jet regimes. So that's what this plot is sort of giving an example of. In the top plot, it's showing what the quasi-stationary wave forcing associated with ENSO looks like in years where you've got a very persistent northern jet. And you see a very strong signal there. But if you look at the kind of the inverse, the years where the southern jet regime is very persistent, you don't get the kind of opposite signal. You don't really get any signal at all, which is telling you that this forcing, the quasi-stationary wave forcing, is projecting onto the northern regime in particular. And then, your winter NAO, things like your winter NAO are just going to be this non-linear combination of lots of different signals that are each projecting onto different regimes in different ways. And again, the regime picture allows you very straightforwardly to build that into your analysis. Okay, process-based. I think I don't have time to talk about this process-based understanding, so I'm going to just hop straight to the final bit. So, okay, we've talked about a bit about topological foundations. I've tried to convince you that you actually do gain some information by taking the Markov chain approach really seriously. Now the last question is, okay, what happens if you try to do this for climate change analysis using, say, the CMIP6 ensemble? And you'll find, if you start thinking about how you might do that, you'll quickly realize that it kind of only works if the following two things hold. Firstly, you need your regimes to be constant in time. So that was a kind of implicit in all the Markov chain stuff we were just looking at. The states will assume to be constant and fixed. So you need stable regimes, right? If your regimes 100 years from now are completely different from what they are right now, then then you're going to be in big trouble with any kind of regime analysis. Secondly, it's no good to do this analysis if your climate models don't actually have these regimes, or if they have regimes that are very different somehow from what the observed regimes are, because then again, it's very hard, if that's the case, to have any confidence in your analysis. And then also, okay, I've talked mostly about these jet regimes, but we do really want some kind of geopotential height regimes, because they contain, the jet latitude is quite a crude metric essentially, and we want to ultimately account for more information. In particular, we really want to have regimes which account for blocking, which is not just straightforwardly captured with this kind of zonal jet latitude picture. But if you take your kind of classical 4Z500 regimes that we saw earlier, they end up failing these criteria quite miserably, in fact. So I'm showing you an example of that using reanalysis data and the plot on the left there. What we've done there, this was done by Josh Dorrington, my colleague. Essentially, you take your k-means clustering, which is how these 4 regimes are found, and you pick a random 30-year time period in 20th century, in the 20th century. And then you do your clustering in that 30-year time period, and you look at where the 4 regimes are sitting, the centroids of your 4 regimes are sitting in your phase space. And this is showing a projection of that onto the first 2 principal components. So each color is somehow, and each dot is showing you the cluster centroid at a different 30-year time period. And what you can see is that they wobble around quite a lot. And in fact, you get these interesting structures, right, where, certain time periods, the regimes are, the centroids are in one place, other time periods they're in another place. You get periods where 2 cluster centroids are overlapping considerably with each other. It's even worse if you do a different projection onto the first and fourth principal component. Basically, these patterns that you get with this 4-state picture are all over the place when it comes to decadal variability. And I'm not going to show this, but you can probably believe me that, well, this is using observed data, and it's considerably messier if you take a climate model, which are kind of usually, as a rule, less stable in the mid-latitude than observations. And in particular, the patterns you get with a random model, if you take a random CMIP6 model and a random 30-year time period, and you compare the patterns you get with the observed ones, you cannot in any way expect to have a good match between the 2. Okay, the problem, it turns out, is jet speed variability. So essentially, when we're looking at geopotential height, things like the NAO, it's basically a combination of jet speed and the position or shape of the jet in one way or another. And the jet speed, it turns out, is this big Gaussian blob, which has a considerable amount of decadal variability and just ruins all your clustering analysis. But okay, the lesson we learned from the first part of the talk is that regimes are somehow meant to be non-trivial structure, right? So if we know that we've got this very trivial, noisy Gaussian component in our system, we might as well get rid of it. And in this case, you can get rid of it just by regressing it away, just straightforwardly regressing it out of each principal component. And the change, what happens then is you move from the plot on the left, which is showing you the 4 classical regimes sitting in your Z500 phase space. You move to the right, where you get much more clearly non-Gaussian phase space, and you get these 3 regimes picked out. And we call these geopotential jet regimes. And what's nice about these regimes is that they are extremely stable, first of all. In this case now, if you pick any CMIP6 model and any 30-year time period, the odds are extremely good that you are going to see the same regime patterns again and again and again. This is also the case if you move forward, if you take some kind of climate change projection from a CMIP6 model, the regimes are essentially stable out into the future as well, which is what we want to see, right? We want changes. We don't want the patterns to change. We just want things like their occurrence rates to change. It's not just that these patterns are really stable, but the CMIP6 models generally all get them right. So now the patterns in the models really do look extremely similar to the observed patterns, unlike in the previous methodologies. And finally, these three regimes, okay, there are three regimes here and three jet latitude regimes, and pleasingly, it turns out that these three geopotential jet regimes, they're like, well, essentially, the jet latitude regimes are like a first order approximation of these three geopotential jet regimes, which essentially cover both jet latitude behavior, but also blocking indices. And you'll have to just take my word for that. This is what they look like, just briefly. You get an Atlantic ridge pattern. So it's familiar patterns cropping up again, right? It's an Atlantic ridge pattern, you get an NEO minus pattern, and you get some kind of blocking pattern. And just to convince you that these really are stable, here's the same projections that we saw earlier using these geopotential jet regimes. And you just see as soon as you get rid of this very noisy jet speed influence, suddenly your clusters are extremely stable. Okay, so I said something in my abstract, right, about how now we can begin to explain model regime performance. So there are several upshots to working with regimes that are super stable and look the same in reanalysis as in models. And one of the clear upshots is that now you have a decent chance of actually understanding, you know, why is one model better or worse than another when it comes to regimes. And here's an example of that. What I've done here is I've computed the average occurrence of the blocking regime for a bunch of CMIP6 models. They're all in dots here. The blue versus red dots is just slightly different CMIP6 scenarios, essentially. And then I've computed for each of those models the kind of average strength of the eddy forcing. And it turns out that these correlate extremely well with each other. So you can now begin to say things like, okay, you know, this model has too little blocking because it has too weak eddy forcing. And you can begin to do this with lots of other model biases and begin to link model biases to regime performance. So that's very exciting and very much ongoing work. And I'll come to my last slide here. Just as a teaser trailer, we're still actively working on understanding future climate change here. But essentially what it looks like, the first view seems to be that the occurrence rates of these regimes don't change in the future, but the persistence seems to systematically go down, which might suggest we're heading for a future with less persistent and therefore also less predictable circulation regimes. And I will stop there. Thank you very much.
Great, thank you so much, Kristian, for that excellent talk. Has anyone got any questions?